Okay, welcome back. This is the second in our series of review videos for Math 1410 Elementary Linear Algebra. I'm Sean Fitzpatrick. In this screencast we're going to review the algebraic properties of the real numbers. This is a course in linear algebra. It's not a course in calculus, so we are not going to concern ourselves with the analytic properties of the real number system that are important for a subject like calculus. If you're interested in that sort of thing, you've got to wait and take a course like Math 3500 where you actually get into the details of the real number system, which, as it turns out, is much harder to define than you might at first think. Okay, so here are some of the sets of numbers that we will encounter in this course and that you encounter generally in various mathematics courses. The natural numbers, we saw those in the last video. The natural numbers are just the positive whole integers, your counting numbers, if you like, 1, 2, 3, 4, and so on, going on forever. One thing to note is that depending on the context and the author, sometimes you will find that 0 is counted as a natural number. Sometimes not. The fact that there's a disagreement doesn't really matter that much. It's not even a matter of a disagreement. The same person might decide that 0 does or does not belong to the natural number system depending on what sort of work they're doing. As long as you specify ahead of time which set you're using, there generally isn't any cause for confusion. Now, the integers are what you get if you take the natural numbers and you extend them so that you include 0 and you also include the negative numbers. So minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on. So you have both positive and negative whole numbers, plus 0. Those together make up the integers. The rational numbers are what you get when you introduce fractions. So we can write the rational numbers using set builder notation. We can say, well, it's the set of all fractions of the form p over q, where p and q are integers, and we know we're not allowed to divide by 0, so let's specify that q here is not equal to 0. That gives us the set of all rational numbers. The real numbers, well, there's no way to really write them down nicely as a set. One way that we tend to visualize the real number system is using the number line. So somewhere in the middle of our number line we put 0, and the integers are in there, right? 1 is in there, 2 is in there, minus 1 is in there, minus 2 is in there, and so on. But of course, all of the fractions are in there as well, so somewhere in between here we have maybe 1/2. 1/2 is in there, 1/3, and or like 47 over 16. Every possible rational number is included in there. But the real numbers also include the irrational numbers. So the irrational numbers include things like the square root of 2, maybe pi, Euler's number e, the base of the natural logarithm. Basically, every possible decimal expansion is included in the real number system. And like I said, the way to actually define the real numbers is quite difficult, and it involves a lot of calculus-based ideas that are well beyond what we will talk about in this course, so we're not actually going to worry that much about how to define the real numbers, and just sort of hope that this is something which is sufficiently familiar to everyone that we can work with them. Now, the complex numbers are something that we'll be considering very soon. The set of complex numbers are all things of the form x plus I times y, where x and y belong to the set of all real numbers, and this funny I here. Well, I is defined to be the square root of minus 1. And I know you're thinking that everyone told you all the way through high school that you never, ever, ever can take the square root of a negative number. Well, this is true if you're working within the real number system. If you take the square root of a negative number, you don't get a real number. But you can move beyond the real number system, and you can consider numbers where the square root of minus 1 is defined. Notice that at each step we actually enlarge our number system. You might note that using the subset notation from the previous video, the set of natural numbers is a subset of the integers, which in turn are a subset of the rational numbers, right? Because I can always set, this inclusion is given by putting q equal to 1 in this definition down here, right? If I set q equal to 1, p over q is just p, so I have an integer. And then, of course, every rational number is in particular a real number, and as I mentioned in the last video, every real number also in turn is a complex number. So all of these sets are sort of nested one within the other. And you can think of each larger set as being something that is created when you want to do some sort of new algebra that didn't work in the old set, right? Moving from the natural numbers to the integers, well, that's something that's necessary if you want to start doing subtraction. If you want to have negatives, if you want to have cancellation when you're doing addition, you're going to need negative numbers. Similarly, moving from the integers to the rational numbers, well, if you want to have inverses when you're doing multiplication, if you want to be able to undo multiplication, if you want to be able to divide, well, then you're not going to be able to work just within the integers. You're going to need to allow for fractions. And then, of course, moving to the real numbers, well, there are certainly plenty of numbers like the root 2, like pi, like e, that can't be expressed as ratios, and so we need to enlarge things a little bit more. And then, you might decide that you do, in fact, need to be able to take square roots of negative numbers, and then along come the complex numbers to allow for that to happen. So as your algebra needs increase, the size of your number system may have to increase along with it. Okay, now, we want to look at the particular algebraic properties that are sort of essential to the real number system and allow us to do the sort of algebra that we're used to doing, right? So there are a number of these properties, and we're just going to write out what these all are. So the closure property is simply the statement that whenever you add two real numbers together, you get a real number. So if A and B belong to R, then their sum also belongs to R. It would be a fairly strange sort of addition if we had some sort of addition operation where we added together two numbers and ended up outside of the number system that we were working in. That would not be a desirable property to have. Commutativity is the fact that the order of addition doesn't matter. A plus B is the same thing as B plus A, and that holds for any real numbers. So among all of the real numbers, there is not one single case where you find two real numbers where A plus B comes out to be different from B plus A. You are safe in working through and knowing that that's always going to come out to be the same thing, right? So we know that 2 plus 3 is equal to 5, and that's the same thing as 3 plus 2. But we also know that it doesn't matter, for things like where we can't simplify, something like maybe 1 plus the square root of 2, there's no way to simplify that expression. But we do know that it doesn't matter whether we write down 1 plus root 2 or root 2 plus 1. Either of those is going to be the same thing. Now, associativity is what lets you take addition, so addition is something that takes two numbers and combines them to give you a third number. But what happens if you want to add three or more numbers? Well, you need to extend this operation to larger sums, and associativity is what allows you to do that, because associativity tells you that if you want to add, say, three numbers together. Well, one way to do it might be to add the second and third numbers, add b plus c. That gives you a number which you can then add to a. Another way you could have done it is you could have first combined a and b to give you a new number and then added the result to c. And associativity says that it doesn't matter. You can do this whichever way and you're going to get the same answer. And this is why when you have large sums of numbers that you want to add together, you don't even need to bother with the brackets, right? Associativity says that placement of brackets doesn't matter, and so if you leave the brackets out altogether, there is no ambiguity. And again, this is something which holds for every real number that you might happen to want to work with. Identity, well, the identity property is simply saying that we know there is a special real number called 0, and it has an interesting property, which is that if you add it to any other real number, nothing happens. And again, it doesn't matter which number a we're talking about here, adding 0 does nothing. So this is the identity property. Finally, we have the inverse property. The inverse property says that if you give me a real number a, then I can find another real number called minus a, and this minus a, this negative, is defined so that when I add it to a, I get 0. Right? So the existence of this inverse, this is of course what we use to define subtraction. Note that we define a minus b by, well, adding the negative of b to a. So subtraction really is defined in terms of addition in this way. And the fact that inverses exist, this is what drives a lot of basic equation solving, right? This is what tells us that we can subtract the same number or add the same number from both sides of an equation and, cancel things out and simplify, right? Because a and minus a, they cancel out to give me 0, and I know that adding 0 to something does nothing at all. So a lot of equation solving is driven by the identity property and the inverse property. Okay. Now, of course, we can consider similar properties for multiplication. The closure property, once again, simply says that the product of any two real numbers is, again, a real number. So a times b is going to be a real number. Usually when we're working with variables like this, we just indicate a product by writing two numbers one next to the other. Sometimes if you're dealing with maybe numbers, maybe a is 1 and b is 7 or something like that, and you still want to indicate a product like this. Sometimes we'll write this with a little dot in between to indicate the multiplication. The one thing that we never use is we usually do not use the x to indicate multiplication. That's not a notation that we use. In this course, the only place where you're going to see that x showing up is when we talk about the cross product of vectors. Otherwise, we generally stick to either just writing them next to each other or putting the little dot in between. Okay. Commutativity, well, you can guess what that means. A times b is the same thing as b times a, and that should hold for any real numbers a and b. And of course, for us, the commutativity of multiplication is just as obvious as the commutativity of addition. This is something that we expect to always happen because we're just used to it from working with numbers since elementary school. One thing that we are going to see later in the course is that actually commutativity is not a universal property. There are other algebras, in particular when we get to the algebra of matrices, we'll see that sometimes order of multiplication can matter. It doesn't matter for real numbers, but it will matter for matrices. We'll see that later on. Associativity, as with associativity of addition, this is the property that lets us extend the operation of multiplication from products of two real numbers to products of three or more by telling us that We can group things however we want. We can place brackets wherever we want, and the result will be the same. And so that means that I could simply just write ABC without any brackets, and this would be unambiguous. Everyone would know what that number meant. Okay, so this again holds in general, no matter what the numbers A, B, C happen to be. Now, what is the identity with respect to multiplication? Well, again, identity is some number that when you perform the operation, nothing happens, and we know that when you're dealing with multiplication, the special number that's involved in this case is the number 1, right? 1 has this special property that 1 times A equals A. For every real number A. And finally, inverses, just as with addition, we use the negation, the inverse with respect to addition, to define subtraction and allow us to sort of do some cancellation there. The inverse with respect to multiplication is what leads us to division. And the rule for the inverse says that if I have any non-zero real number, then there is going to be a new number, often written like this, a to the exponent of -1, and you might also write it as a reciprocal 1 over a. And the defining property here, just as if we jump back, remember that the defining property for the additive inverse is that you combine the inverse with the original number and they combine to give you the identity. Similarly here, A times A inverse, A times 1 over A, should give you 1. Right? And this is what allows us to define division. If we want to do A divided by B, we define that to be A times 1 over B, so A times B inverse. This is how division is defined. Alright, so those are all the properties that addition and multiplication have, and you'll notice that they're pretty much all the same. The only one to be careful of is that with multiplication, of course, we can't divide by 0. So every real number has an inverse with respect to addition. With multiplication, there's one real number that doesn't have an inverse, and that's 0. Okay. Now, we also want to know, how do addition and multiplication interact? Can you combine them? Well, we know that we can. We know that we have this distributive rule that says, well, if you give me any real numbers A, B, and C, if I want to do A times B plus C, that's the same thing as A times B plus A times C. Okay, that's the distributive property. We could, although it's redundant because we have the commutative law for multiplication, it still doesn't hurt to sort of see it from either side. So we can either distribute to the right, but we can also distribute to the left. So A plus B times C is the same thing as A times C plus B times C. So we can write that either way. Okay, so this is called the distributive property, and it tells you how addition and multiplication interact. And the distributive property is quite important, and it's something that you use a lot without really thinking. So for example, when we write something like 3x plus 5x is equal to 8x, well, why does that work? Why does this sort of grouping that we do when we simplify expressions, why is that allowed? Well, this is allowed since 3x plus 5x. If we run this second distributive property, this guy here, we run that backwards, then 3x plus 5x, well, that's the same thing as 3 plus 5 times x. Notice that basically when you run the distributive property backwards, going from right to left instead of right to left, the distributive property in reverses. just factoring. So we factor out an x, and then of course we know that 3 plus 5 is equal to 8. So we get 8x, right? So this is all due to the distributive property. So it seems like an abstract thing, but it is something that you use every day without even really thinking about the fact that you're using it. It's there, and just like with all these other properties, they drive the algebra, right? So none of the usual algebraic manipulations that you use every day that you're used to would work without these properties. And of course, I guess the other thing we could add here is that, well, if you apply the distributive property twice, if you kind of combine both of these, we get our old friend FOIL, this rule for multiplying binomials that says if I want to do a plus b and multiply by c plus d. So the FOIL stands for first, outside, inside, last. So you multiply the first two terms together, a times c, then you multiply the outside terms, a times d, then you multiply the inside terms, b times c, then you multiply the last terms, so b times d, right? And you end up with 4 terms in total. This basically comes from applying, well, these two distributive properties. So if I wanted to write an intermediate step, I would say, well, this is actually equal to a plus b times c, and then a plus b times d, using this first guy here, where the instead of just having an a on the left, I've got a binomial, and I distribute the binomial on the left through the binomial on the right, and then I can use the other version of the distributive property to push the c and the d through, and I end up with my 4 terms. Okay. Now, we did mention that the real numbers are somehow special, right? One thing you can notice as you go through all the algebraic properties is that every one of these algebraic properties that's true for R is also true for Q. Each one of these properties holds in both systems. So algebraically you feel like they should somehow actually be the same, but they're not quite right, because we know that there are some equations which we can solve in Q. If I give you, say, x squared equals 4, well, that's an equation I can solve in either number system, right? I'd say, well, x equals 4, that implies that x squared minus 4 equals 0. Using the distributive property in reverse, I can factor x plus 4 times x minus 4 equals 0, and then I would solve, right? Oh, you probably noticed that I messed up. Those shouldn't be 4s, should they? They should be 2s. And so then I can conclude that x must be either plus or minus 2, because either the first guy is 0 and x is equal to 2, or the second one is 0 and x is equal to minus 2. On the other hand, so that works, this works in either R or in Q. But if I wanted to solve, let's say x squared is equal to 2, so x squared minus 2 is equal to 0, well, over the rational numbers, I actually can't factor this polynomial. There's nothing more I can do. I'm stuck at this point. I have to stop. Over the real numbers, I'm allowed to take square roots, and so I can write this as x minus the square root of 2 times x plus the square root of 2 equal to 0. And I can say, well, that must mean that x is equal to plus or minus the square root of 2. Okay. And so this is something which we can only solve over the real numbers. We can't possibly solve that over the rational numbers. Now, this sort of distinction alone isn't what makes the real numbers the real numbers. As I said, there are other more subtle issues that you would consider in a calculus course, but that's not something that we're going to look at. Now, just to throw this in, because we're going to be getting to it soon, the other thing you could ask about is, well, what about x squared equals minus 4? That's something that has no solution. in the real numbers. But if we allow ourselves to work over the complex numbers, we would find that x is equal to plus or minus 2 times I in the complex number system. So we'll be looking at examples like that coming up pretty soon. Okay, the last thing to mention on this video, we'll try to get things over with right away. In the previous slide, when we're solving these systems, right, when we get to this factored form and we conclude that x must be either plus or minus 2, what is letting us do that is the special properties that 0 has when it appears in equations. Now, we do know, for example, that 0 times a is always equal to 0. This is something which is always true. If you want to try and understand, here's a good exercise for you to try. Why is 0 times anything equal to 0? See if you can play around with just the axioms that we've introduced and see if you can deduce that 0 times a must in fact be equal to 0. Here's a starting point. Well, remember that 0 plus anything equals 0. So in particular, 0 plus 0 is equal to 0. So 0 plus 0 times a is the same thing as 0 times a. Now expand that left-hand side using the distributive property, and then use the fact that you have additive inverses to do some cancellation, and you should be able to show that 0 times a is in fact equal to 0. The other side of the coin here is that if I have a product which is equal to 0, I'm forced to have one or the other of those numbers equal to 0. Right? There's no way to multiply two non-zero numbers together and get 0. And that is what lets us factor and solve, like on the previous slide, right? Because if I know that this product x plus 2 times x or x minus 2 times x plus 2, if I know that that product is 0, I know that either x minus 2 equals 0, and then I get the positive root, or I know that x plus 2 is equal to 0, and then I solve for the negative solution, x equals minus 2. So I know that one or the other has to hold. Okay. If you want to understand why this is true, just notice that, well, if a is equal to 0, then you've done your job, right? It's going to hold. If a is equal to 0, then a times b is 0. If a is not equal to 0, and you know that a times b is equal to 0, well, then you can multiply both sides. If a is not equal to 0, then it has an inverse. So you can multiply both sides by 1 over a. And the a's will cancel out, and you'll just be left with plain old b equal to 0. Okay. Finally, it's always important to mention that if you're dealing with fractions, and we'll review fractions on the next video, it's perfectly fine to have 0 in the numerator. 0 divided by anything is just 0. You only run into trouble if 0 is in the denominator. Anything divided by 0 is undefined, including 0 divided by 0. So watch out with that when you're dealing with fractions. Make sure that you don't divide by 0. Okay, so that's everything for this video. We'll pause here.